I want to demonstrate another technique that benefits from Maclaurin series and Taylor series. We've previously looked at indefinite integration. You can calculate an indefinite integral, and even if the antiderivative can't be expressed as a finite combination of elementary functions, then maybe a power series will do. Today, I'm going to be looking at definite integrals. So I have two examples prepared. The first of these, I'll be looking at the integral from 0 to 1 of the function sine of x to the power 4. Now, of course, computer calculation, and Desmos in particular, is able to just do this very quickly through numerical methods. The answer being 0.1875 and change. Now, there is a question about what exactly is going on under the hood. What kind of mathematics allows this calculation to even work? And frankly, I don't know because I didn't program this website. I might suspect they are using Simpson's rule or something similar for an efficient computation. But the point of this video is to show how Maclaurin series can be used to calculate things like this. So what I'm going to do, since I don't really want to find an antiderivative of sine of x to the power 4, is I'm going to turn it into a Maclaurin series. And the way I'm going to do that is by using the Maclaurin series for just the regular sine function. So I know that sine of x is equal to its Maclaurin series. I'll have the sum n from 0 to infinity. Desmos is going to get a little upset with me because it only likes finite sums, but that's okay. I'm just using it to write out the formula neatly. My summands have coefficients minus 1 to the power n over 2n plus 1 factorial. And then this is times x to the power 2n plus 1. Now, this is a fairly common Maclaurin series, but it's not quite the function that I'm interested in. So what I'm going to do is I'm going to manipulate the left-hand side of this equation. And I'll say that I'll replace x by x to the power 4, because that's the actual function I want to see. On the right-hand side, if I want to keep everything balanced, then I need to raise this x to the power 4 as well. So now I have x raised to the power 4, and then raised to the power 2n plus 1. That looks a little much, but I can use the laws of I can use my exponent laws to simplify that. If I raise a number to a power and then raise it to another power, I can simplify my formula just by multiplying the two different powers. So 2n plus 1 times 4 gives me 8n, there we are, plus 4. So this integral should be equal to the integral of the sum. Again, Desmos doesn't like this very much because it's an infinite sum. But what I can do from this point, because this series converges to sine of x to the power 4, is I can switch the order of the integration and the sum, the integral sign and the capital sigma, like this. Now, this is a very nice thing to do because I actually know how to compute integrals of powers of x. For expressions like this, I'm working my way from inside to out. I'm ignoring that sigma for just a little while. And I know the antiderivative of x to the power 8n plus 4. That's going to be x to the power 8n plus 5 divided by 8n plus 5. So I'm copying this over as if I was working on a piece of paper. And you can see why I'm not using the screen drawing for this today. So I might see something, I don't like that so much. Let's put a times in there just to keep things tidy. 8n plus 5. Now this all has to be evaluated still. I have to plug in my 1, and I have to plug in my 0, and I have to subtract. Well, when I plug in 1, I'll just have 1 to the power 8n plus 5, which is 1. And when I plug in my 0, right, I'd have to subtract the same fraction, but with numerator 0 to the power 8n plus 5. Oh, well, that's just 0. Cool. So this sum right here should give me the value of this integral. Now, this is an infinite sum. So it's nice that theoretically this number here should be equal to this number up top. But how do I turn this into a practical computation? Well, I notice that the sum that I've got written here on line 5 is an alternating sum. And I can actually predict how close an alternating sum will be to the actual value of my integral, right? If I truncate, if I take the partial sum, there's a nice formula that tells me how far off I will be. So if I stop at the number n, right? So add up the number 0 fraction, the number 1 fraction, the number 2 fraction, and I stop at some n, my margin of error is determined by the very next term in the series. That's a special property of alternating sums. We've seen that previously. So I'm going to calculate how big is this fraction where I've got minus 1 to the power n plus 1. I'm dividing by 2n plus 1 factorial. And then I'm multiplying by, I guess, 1 divided by 8n plus 5. So however big this fraction is will tell me the margin of error for my partial sum in approximating the alternating series. So if n equals 0, my margin of error will be 0.2. N equals 1, my margin of error will be 0.01. N equals 2, my margin of error will be 0.0003. This is a pretty simple thing to do. Now, for this problem, I would like to have a margin of error of 0.0001 or less. So I'm not there yet. It looks like I need to go out one further. If I take the n equals 3 partial sum, my margin of error should be this very small number here, 0.000006. So I only need the number 0 fraction, the number 1 fraction, the number 2 fraction, and the number 3 fraction. Yes, to approximate my integral. Now, let's write that out. If n equals 0, my numerator will be 1. I'll divide by 2n plus 1 is 1 factorial. And then I've got 1 over 8n plus 5. If n is 0, then this will be over 5. Okay, that's my number 0 fraction. Let's add on the number 1 fraction. Oh, excuse me. Let's add on the number 1 fraction. For the number 1 fraction, I've got negative 1 to the power 1. I'm dividing this by 3 factorial. I'm multiplying by 1 over 13. Okay, let's add on the number 2 fraction. The number 2 fraction has -1 squared in the numerator. That'll be positive. Divide by 5 factorial. Multiply by 1 over n is 2. So I'll have 16 plus 5, which is 21. And then for my number 3 fraction, which is where I'll be stopping, my numerator has a -1 cubed, which is still negative. My denominator for my number 1 fraction, for my number 3 fraction, glad that I'm saying this stuff out loud as I go, will be 7 factorial times 1 over n is 3, 8 and 3 is 24. When you multiply them together, plus 5 is 29. So my approximation is 0.1875. And compared to the value that Desmos gives me, 0.1875. Looking good. Excuse me, gosh. Sorry, I just ate. This is looking pretty good. I add up 4 fractions, and I've estimated the value of this integral. The thing that's letting me do this is turning my function into a power series and then integrating each term of the power series individually, just like a polynomial. Now, I want to do another example. So let me clear all of this stuff. So instead of integrating from 0 to 1, I want to go up to this number from 0 to 0.1. And this is going to be an integrand of 1 plus x cubed raised to the power 1/2. And Desmos tells me that this is about 0.100012 and change. And again, calculators are ubiquitous. The purpose of this exercise is to show how Maclaurin series can be used from a theoretical point of view. If you want to use these things for practical calculation, you will likely be working with functions much, much more complicated than the square root of a polynomial, right? We can just use numerical methods like what Desmos is doing right here. But because this demonstration would be so much harder to watch, if I really had one of those messy functions in my integrand, we'll have to make things simpler and focus on series that we can actually compute. Now, the series I'm going to use for this demonstration is the binomial series. Anytime I have the quantity 1 plus x raised to any power, I can write it out using the binomial series. So again, it's a sum, and from 0 to infinity. And my coefficients here have a special formula, right? I'll still have x to the power n. This is a power series, but the number that goes here is called the binomial coefficient. And I'm just, aha. So Desmos implements this as NCR, and I'm curious to see if they allow Yes. 1 equals. No, that's not quite what I'm looking for. Sorry. So I'm going to use the following notation. If I was at the board, I would do something a little bit different. I'm going to call this the function c, which has two inputs. The first is the number 1/2, which is my exponent over here. The second of these is n, so I'll get a different coefficient for each value of n. On the board, I would write this out in parentheses. I'd have a 1/2 up top, and I'd have an n at the bottom. And what this number is describing a fraction whose denominator is the factorial number, n factorial. And the numerator is trying to be a factorial number as well. So I'd have 1/2, and then I'd have minus 1/2, because that's the number that's 1 less than 1/2. I'd go 1 less than 1/2 again and get -3/2. And I just keep going until I have n different numbers on the numerator. Oh, it's all right. So that would be 1/2 minus n plus 1. Now, as I'm working here, I'm going to do the very same thing as in the previous problem. I'm going to change this formula to make it match my integrand. The only thing I have to do is I have to cube the x I see over here. And on the right-hand side, I've got to cube that x as well to keep the equation balanced. Now, I can grab a copy of this integral, and I'm going to replace the integrand with the power series. And once I do that, I'm going to put this capital sigma on the outside, which lets me do my integral on each different power of x separately. I'm working from inside to outside. For right now, these coefficients are just numbers. It's just some constant multiple. When it comes time to figure out a value for this thing, I can do it using this formula here. But for where I'm at in the Scratch work, I'm not going to evaluate it just yet. So I know the antiderivative of x to the power 3n. It's x to the power 3n plus 1. Let me put that up. Oh. Let me put that up here in the exponent. And then this is going to be divided by 3n plus 1. And again, I've got to evaluate this at the two different endpoints of my integral, 0.1 and 0. So I'll have this fraction here with numerator 0.1 to the power 3n plus 1. And I'll subtract this fraction over here with numerator 0 to the power 3n plus 1. Oh, well, then I'm just going to get rid of that 0 piece. So now it comes time to figure out my margin of error. How far do I have to go to approximate this function? This is where I really do need to evaluate my binomial coefficient. So rather than use a slider, I'm going to be putting these in by hand. The very nice thing about this series, though, is this is still an alternating series. Why is that? Well, in this formula, my binomial coefficient, 1/2 and 0, well, by definition, if n is 0, the binomial coefficient gives you a 1. If n equals 1, then my numerator will be 1/2, my denominator will be 1 factorial. And what's going to happen is that as my n gets bigger, I'm multiplying by more of these fractions on the numerator. But more to the point, those fractions are each going to be negative numbers. So my number 2 binomial coefficient is going to be negative. This is the number negative 1/8. Then my number 3 binomial coefficient is going to be positive. My numerator is 1/2 times minus 1/2 times minus 3/2. It's all divided by 3 factorial. So this is going to be a positive number. And after you work out the cancellation, this is positive 1 on 16. So besides the number 0 binomial coefficient, for an exponent of 1/2, these will be alternating from positive to negative. So I can use my alternating series approximation. So let's say I did stop at fraction number 1. Well, I'd be using the number 2 coefficient to estimate my error. My error will be based on this size, so negative 1/8 times 0.1 to the power n equals 2, so that'd be to the power 7, and divide by 7. Again, this is from using the estimation formula, stopping at the number 1 fraction in the series. And my margin of error here would be a little bit bigger than 10 to the minus 9. So add up the number 0 fraction plus the number 1 fraction, and I should have 8 significant figures of accuracy here. Let's actually check that that all works out. So for my number 0 fraction, this binomial coefficient will be the number 1. I'm multiplying by 0.1 and I'm dividing by 1. Okay. For my number 1 fraction, I'm using the number 1 binomial coefficient, which is 1/2. I'm multiplying by 0.1 raised to the power 4, and I am dividing by 4. So my approximation here, using 2 fractions, is that the integral should be about 0.1000125. Let's check. The actual value of the integral is 0.1000129. That's real nice. So this method lets me turn an integrand that I don't want to mess with too much from an antiderivative point of view into a power series. And then depending on how well my Taylor polynomials approximate the function I care about, I can get some very nice integrals here with not a whole lot of computation, once I know what formula I'm looking for. All right, I'll catch you later.